The Haldane effect is a property of hemoglobin first described by John Scott Haldane. Deoxygenation of the blood increases its ability to carry carbon dioxide. This property is the Haldane effect. Conversely, oxygenated blood has a reduced capacity for carbon dioxide. Carbamino. Carbon dioxide can bind to amino groups, creating carbamino compounds. Amino groups are available for binding at the end-terminals and at side chains of arginine and lysine residues in hemoglobin. This forms carbaminohemoglobin. Carbaminohemoglobin is the major contributor to the Haldane effect. Buffering. Histidine residues in hemoglobin can accept protons and act as buffers. Deoxygenated hemoglobin is a better proton acceptor than the oxygenated form. In red blood cells, the enzyme carbonic anhydrase catalyzes the conversion of dissolved carbon dioxide to carbonic acid, which rapidly dissociates to bicarbonate in a free proton. CO2 plus H2O H2CO3 H plus HCO3 minus by Le Chatelier's principle. Anything that stabilizes the proton produced will cause the reaction to shift to the right. Thus the enhanced affinity of deoxyhemoglobin for protons enhances synthesis of bicarbonate and accordingly increases capacity of deoxygenated blood for carbon dioxide. The majority of carbon dioxide in the blood is in the form of bicarbonate. Only a very small amount is actually dissolved as carbon dioxide, and the remaining amount of carbon dioxide is bound to hemoglobin. In addition to enhancing removal of carbon dioxide from oxygen-consuming tissues, the Haldane effect promotes dissociation of carbon dioxide from hemoglobin in the presence of oxygen. In the oxygen-rich capillaries of the lung, this property causes the displacement of carbon dioxide to plasma as low oxygen blood enters the alveolus and is vital for alveolar gas exchange. The general equation for the Haldane effect is H plus HbO2 H plus Hb plus O2. However, this equation is confusing as it reflects primarily the Bohr effect. The significance of this equation lies in realizing that oxygenation of Hb promotes dissociation of H plus from Hb, which shifts the bicarbonate buffer equilibrium towards CO2 formation. Therefore, CO2 is released from RBCs. Clinical significance. In patients with lung disease, lungs may not be able to increase alveolar ventilation in the face of increased amounts of dissolved CO2. This partially explains the observation that some patients with emphysema might have an increase in PaCO2 following administration of supplemental oxygen even if content of CO2 stays equal.